Hello, this is Eric Fielding of the Jet Propulsion Laboratory, Pasadena, California. I apologize for not being there in person to give this presentation. I found out 2 days ago that I have positive for COVID and I do not want to go there and infect others. I apologize also for the roughness in my voice due to the ongoing COVID infection. I will be talking today about the Hayward Fault that many of you know runs through the urban area of the eastern San Francisco Bay in California. This work is a collaboration with many people at the USGS, University of California, Berkeley, JPL, and the University of Houston. I would like to acknowledge many others who have contributed in acquisition and processing of data used here and have supported this work over the years. The overall goal of our fault slip project is to understand fault zone properties that affect earthquake risk in continental strike slip fault zones that are hazards in many places around the world. We focus on the Hayward Fault as it is one of the highest risk faults in California and it has been studied in with many methods. I will only talk about geodetic measurements of surface displacements in this brief talk. The Hayward Fault is part of the plate boundary between the Pacific Plate and North American Plate, portion that's represented by the Great Valley Sierra Nevada block. The Hayward Fault shares the strain of the plate boundary with the San Andreas Fault to the west and the Calaveras-Concord Fault system to the east. We use surface displacement measurements measured with GPS, INSAR, and other methods, and a computer model of elasticity to relate these surface measurements to fault behavior at depth. European Copernicus Sentinel-1A and B satellites have acquired data over this area since 2015. The ARIA system at JPL has processed 962 geocoded unwrapped interferograms, also called GUNW, that we put into the time series analysis software called MintPy. No tilt or ramp adjustment was applied to this dataset, and this map shows the linear mean velocity over 7 years. Coherence is low in areas of vegetation, especially in the Santa Cruz Mountains, East Bay Hills, and Sacramento River Delta. I used a fault slip model to model the interseismic slip by putting deep faults slipping uniformly at depth and locked in the upper 12 kilometers based on the Bergman et al. Geology 2006 paper. This map shows the predicted horizontal surface displacements from that deep slip model. To more efficiently work with the Sentinel-1 INSAR data, I downsampled it with a scheme that optimizes the resolution of the slip on the Hayward and Calaveras faults. The top panel here shows the sampled INSAR data. The middle panel shows the interseismic model that I just showed in the last slide projected into the radar line of sight on those same sampled points. And the bottom panel shows the residual, that's the difference between the predicted displacements from the GPS deep slip model and the INSAR, and the large scale trend here is flat. That indicates that the INSAR and the GPS interseismic are highly compatible at the large spatial scales. The smaller scale variations close to the Hayward Fault are due to the shallow creep on the Hayward Fault. While the Sentinel-1 data is excellent at the large spatial scales, it does not provide the detailed information on what's going on at the uppermost few hundred meters of the Hayward Fault. For that, we've been acquiring data with the NASA UAV SAR radar system. It's an interferometric SAR that flies on a piloted Gulfstream 3 airplane. The system is an L-band, 80 megahertz, very high resolution, fully polarimetric radar, and we've been acquiring data over the Hayward Fault since February 2009, with the last acquisition in November 2023. We're hoping for another acquisition later this year. In general, we've been getting data 2 to 3 times a year due to the cost of flying the airplane. It's not possible to do more frequently than that, but because this has a very high resolution, approximately 1.2 meters in the range or cross-track direction, and 0.6 meters or 60 centimeters in the along track or azimuth direction, the resolution of this data is much higher than what we get from the Sentinel-1 satellite images. The co-registered SLC stacks are available from uavsar.jpl.nasa.gov for those who want to analyze this data. We take the SLC stacks processed by the UAVSAR team and load those into the ICE2 strip map stack workflow to do the rest of the INSAR processing, including multi-looking, phase unwrapping, and filtering. Then we load the interferograms into the MintPy SBAS time series analysis, same thing that we used for the Sentinel-1 time series analysis, to estimate the time series. This map here shows the temporal coherence of time series for the various strips over the area. Temporal coherence depends again on the vegetation and on the steepness of the slopes. There's a total of 5 UAVSAR flight lines that are running in the flight heading 055 northeast direction. The airplane looks off to the left, so these have the radar beam looking to the northwest along parallel to the Hayward Fault. These 5 tracks have been processed to time series and mean velocity, and we can see the discontinuity due to the approximately 7 millimeters per year of surface creep on the Hayward Fault. There's a variation across the swath because the incidence angle varies from the near range on the southeast side of the swath to the far range on the northwest side of the swath, where it's more sensitive to the horizontal motion. We similarly have a set of lines where the airplane is flying the opposite direction, heading 235 degrees, and looking with the radar looking to the southeast. These lines have the opposite sensitivity to the horizontal motion, and a similar variation across the swath. This map shows a detail of the UAVSAR mean velocity map combined with the temporal coherence map in grayscale. The areas of dark colors mean that those areas are either covered with trees or the ground surface has changed too much during the time interval between 2009 and 2019. These large black areas in the south are the areas of the Tesla factory and associated housing developments. This curved line that runs across the Hayward Fault is the Interstate 680 freeway. In this area, we have 2 areas of detailed ground measurements, including the creep meters installed by Roger Billum at the Gallegos Winery, former Gallegos Winery, shown by the green dot, and a set of mobile laser scanning measurements made by my colleague Ben Brooks Brooks and colleagues at the USGS along this red line down here. On the top right, I show a plot of a profile through the UAVSAR data shown by the light gray dots, and compare that to a fit to the creep meter data shown by the dark blue dots, and the foundation offset rate shown by these cyan dots. The red line shows a screw dislocation fit to the UAVSAR data with a rate of 10 millimeters per year and a locking depth of 22 meters. So this is showing that the slip at this location is occurring very close to the surface, and the UAVSAR and surface measurements match very closely. The lower plots show another cross-section through the UAVSAR at the top at the Gallegos winery, and a comparison of that to the UAVSAR profile at the Camellia Drive location. We can see that while the Gallegos winery has this very sharp discontinuity and the surface displacements measured from UAVSAR, the Camellia Drive site has a more gradual trend, which is approximately 200 to 300 meters wide. So in this location, we believe that the either the strain is occurring over a 300 meter width, or the upper part of the fault is locked and it's being elastically strained. Further modeling will try to determine which is the case. In conclusion, these high-resolution geodesy measurements enable surface displacements to be mapped at very high resolution and to constrain the near-surface deformation. INSAR from the NASA UAVSAR system provides 15 years of Hayward fault measurements. The coarser satellite INSAR measures displacement at a larger scale due to the deeper strain. We are working to use these measurements to measure how the Hayward fault properties vary along strike and with depth. And we will be looking forward to the new NASA ISRO SAR mission that should be launched early in 2025, which will add new satellite INSAR measurements to this area with high resolution. Thank you very much. I understand that there's no way for me to answer questions remotely, so please send your questions to me at this email address listed on the screen. Thank you.